So now we get to the fun bit of the course. We'll look at some more vehicle designs, and we'll also look at the significant applications that are proposed for some of the vehicles that you've already been introduced to. This first personal air vehicle, which we propose for air taxi use, actually uses third generation engines. It uses 4 fixed third generation engines, which are giving a specific thrust of 1.638 kilonewtons per kilowatt, as opposed to the 4 kilonewtons per kilowatt of the 4th generation, much larger engines that we've looked at before. We still have 2 cavities per engine, so a total of 8 cavities, which can actually be used to give 2-for-1 redundancy. You can see that because it's operated in air, we don't need any liquid oxygen tanks. And the basic design, you can see, is using the thrust frame above the center of mass of the vehicle, basically so that it's an inherently stable design. It's a fairly small, simple, low-cost design that we believe could be used not only to provide a revenue stream for later development programs, but also provide a demonstration vehicle during the 4th generation development programs. So could provide this useful interim step for the full 4G development. Because they're fixed thrusters, the flight controls would be simply an update of the demonstrator UAV that we've also looked at before. And I would suggest that autonomous operation would be eventually offered as an option. Okay, the beauty of EmDrive for the sort of air taxi application is that you can get door-to-door operation. These are small vehicles that will land outside on the road, can pick you up, take you off anywhere else you want to go, and deliver you door-to-door. The fact that you have no downwash from what would otherwise be a rotor-driven air taxi, which is the conventional approach, means that literally you can take off and land vertically just about anywhere. Somebody's back garden, car park in a shopping centre, wherever you want to get from door to door, this personal air vehicle will take you. We've got a low takeoff mass of less than a ton, 940 kilograms. It carries 2,400 litres of liquid hydrogen, and as you can see, is a 2-person payload. Because we're limiting the altitude and indeed the operational distances, we keep to a flight velocity, maximum velocity of 230 kilometers per hour. And because it's 3G operation, we're keeping the maximum acceleration down to 0.4 G. The short flight distances mean that we can limit the maximum flight time to about 2.5 hours. Now, as with the 4G engines that we've proposed, we would have standby liquid hydrogen tanks, 1 per thruster. And these, together with emergency batteries fitted at the base of the vehicle, we would allow about 10 minutes operation for an emergency landing if we lost all fuel. The very stringent safety requirements on any vehicle proposed for operation in the public domain means that we would suggest a ballistic parachute is incorporated so that the vehicle would in fact withstand an all engine out emergency landing. We'll look now at the sort of missions that we can use our deep space probe for. You'll remember that we've already talked about this vehicle, and we'd originally proposed it as mainly for science missions right out to the edge of the solar system. The picture shows the probe in orbit around Jupiter, and essentially we can use the probe to reach any of the planets in the solar system, and the table below the picture shows the flight times to get to the mean distances of any of these planets. So, for instance, we can send a 500 kilogram payload. We can send it to either fly by a planet, to orbit the planet, or indeed even land on the planet. And we're suggesting flight times between, well, less than 5 days for Mercury and Venus, out to slightly less than 190 days to get out to Pluto. Now, I stress these are for flight times for the mean distances of the orbits of these various planets. If we want to go right out to the edge of the solar system, the so-called heliopause, which is about 200 astronomical units out, then we can even reach that in 402 days. It's worth mentioning that if you use conventional electrical propulsion, which has actually been proposed for a heliopause mission, the shortest time they predicted for this was actually 23.8 years. Now, for missions like that, this would generally take up most of any scientist's career, which is a little bit limiting, really. So if you can reduce it down to 402 days, then you can pack in a number of projects for the average scientist's career, which must make it very attractive for use by government and university science departments, which would also be attracted by basically the low cost of the vehicle, and in particular the simple ground launch using the back of a truck. So it makes for a much more modest budget for any of these science missions. So now we'll look at a further application for our deep space probe, and this is the potential large market that exists when we're talking about asteroid mining. And in particular, we would put forward the deep space probe for the prospecting period of any asteroid mining project. A typical 45-meter wide asteroid has been predicted to contain 30 tons of platinum group metals, which current day prices is worth about $1 billion. So we're talking about very high value missions to actually carry out mining on an asteroid. But first you've got to find the right asteroid, and this is where you need probably a large number of prospecting missions which needs a fairly cheap, easily launched vehicle to carry out this part of the mining operation. Most of the asteroids lie in a belt between about 2 and 3¼ astronomical units from the Earth, and this belt contains 93% of all the asteroids. But first you have to find the right asteroid, so the prospecting mission would be typically involve a distance of 255 million kilometers from the Earth. We'd assume a ground launch and a 500 kilogram lander payload, and this probe would then accelerate for 1.6 hours up to a velocity of 363 kilometers per second. It would then cruise for 194 hours and decelerate for 1.3 hours. So literally an 8-day flight to get you into orbit around the asteroid and to start a remote sensing program while you're in orbit. But you can see that the diagram that we show here shows that we have a lander carried by this deep space probe. It's actually mounted in an inverted configuration at the top of the probe. But once you've decided where you want to land, then you would actually fly the lander in the correct attitude, with the thruster above the main payload to give an essentially stable configuration. You would have, we estimate, a fuel margin of 250 kilograms left, which would be held in the small lander tank, and this would cover liquid hydrogen boil-off and in-orbit maneuvers, but would also enable a landing and a number of flights between potential prospecting sites. At each of these sites, you could carry out a detailed geophysical survey, and you can see that in the diagram we've shown that the lander will carry sensor beams, deploy these beams out from the main lander, and also a surface drill to enable pretty detailed surveys to be carried out. We'll now look at using the deep space probe in an asteroid deflection mission. Now, this may well be an absolutely critical mission for human survival, so we can describe it really as an existential mission. And what we've analysed for is a ground-launched probe with 0 payload mass. So you can see the ground launch configuration in the picture, showing it being launched from a tube on the back of a truck. So you can have a fairly rapid response once you've got an alarm raised by any asteroid monitoring organisation. You can, if you want an immediate deflection, you can simply launch flight time of 3 hours, acceleration period of 3 hours, and of course the flight time would depend on how far out you've actually detected the asteroid, but we've said 8 days to the asteroid belt. So we're talking about a pretty rapid response using the deep space probe. Importantly, if you accelerate for a full 3 hours, the kinetic energy that you would get on impact with the asteroid is calculated as 1.15 by 10 to the 9th megajoules. Now, this is a huge kinetic energy release, and you can judge how big it is by comparing it to the Hiroshima bomb, which had 16 kilotons of TNT, whereas the asteroid deflection would release 273 kilotons of TNT equivalent. So that is a pretty big bang, and if you were desperate and wanted to totally destroy the asteroid, this is what you could do. However, if you look at the diagram we've shown, the plot, you can see that the kinetic energy that you get on impact depends basically on the time you spend accelerating. And of course, if you wish to scale back the acceleration period, then you can trade it off for payload mass. And in this way, you can trade off the kinetic energy that you release against the momentum that you would impart by increasing the payload mass, but obviously lowering the velocity on impact. The ability to carry out this variation would be very important, because in practice we would envisage that there would be a significant time period between detecting the asteroid and actually the predicted time of impact on the Earth. And you'd use this period, we believe, to launch a number of probes out towards the asteroid, starting with probably a very small impact release of kinetic energy, and you'd build up this value of kinetic energy on impact until you've actually achieved the deflection you want. And this enables a controlled approach to deflecting an asteroid, rather than just firing it off once and blowing it to pieces, which might not actually be what you want to do if you've got an asteroid of a particular construction, which would easily fly apart. So the ability to fly a number of missions, we believe. So a second application which addresses what is essentially an existential problem for humanity is how you provide the increasing electrical power requirement for the planet without causing it to be overheated. And for many years now, people have put forward the concepts of solar power satellites, but each of the studies to date has shown that the cost of launching these very large structures particularly into geostationary orbit where they're required, it makes the whole projects economically unviable. So one of the earliest applications that we proposed for the heavy launch vehicle was to actually launch sections of a solar power satellite to geostationary orbit. And we came up with a launch cost of $8.4 per kilogram using the heavy launch vehicle. And this is compared to the best current cost of about $1,000 per kilogram if you use conventional launch vehicles. So you can see that suddenly the economics of solar power satellites, particularly the launch costs, are no longer really a problem. You can see that the solar power satellite in the diagram basically consists of two large circular arrays. There is a 3.6 kilometer solar array, which actually captures the sunlight and produces DC electricity, and then a smaller 1 kilometer microwave antenna array, which is used to beam the power back to Earth, basically using a 5 gigahertz phased array antenna. This assembly, as you can see from its dimensions, is going to be pretty heavy, but we've addressed the mass problem by utilizing flexible 136 micron Kapton elements to form actually both arrays. These flexible segments are sort of held by semi-rigid spokes, but at the end of each spoke there is a space tug which is providing continuous tension to the whole assembly. This is enabled using first generation EmDrive thrusters, and we actually addressed the space tug in our lecture 7. The truss structure carrying DC power actually joins the two circular arrays together, and the total mass of this particular assembly is 2,606 tons, our estimate. Now, we reckon this would take 44 heavy launch vehicle missions, and one of the other advantages of using a heavy launch vehicle is you can launch it directly from a small area of tarmac outside the manufacturing site of the SPS elements. So not only do we achieve low launch costs, we achieve a low total mass of the satellite itself, and we enable minimum transport costs when you're moving the elements of the solar power satellite from the manufacturing site to a launch site. You know, what's not to like about it? The antenna itself would be comprised of microwave elements which are actually printed onto a flexible substrate in a very similar material to the actual solar array, which has its solar cells printed on as well. We've done a mass budget, and this is shown in the table below. And you can see that the array, the solar array, requires 40 spokes and therefore 40 tugs. The antenna segments, there's 10 of these, and they would require 10 space tugs. And the tugs, as you'll see in the next slide, not only provide the tension to both these circular arrays, but they also provide attitude control, and they also provide a propulsion to counter the significant solar radiation pressure that will be applied to these very large arrays. Now, an interesting method of deploying these arrays is to use a 100-meter diameter central hub, which itself is deployed using origami method. Now, this has already been tested by NASA in their telescope Starshade project. And these hubs basically would have 2 tugs to provide attitude control during the assembly of the whole solar power satellite itself. There are 2 major problems with solar power satellites, and they both can be addressed by the use of these EmDrive space tugs. First of all, as we've mentioned, you have to provide a counter thrust against the radiation pressure from the sun, and you must also control the attitude of the satellite as it changes requirements over a 24-hour period. So if we first look at the radiation pressure problem, we've calculated that the total pressure on the two large circular arrays amounts to 127 newtons. We have a total thrust available from all the tugs of 270 newtons, so we have a pretty good margin for the small thrusts necessary to very slowly control the attitude of the whole satellite. If we look at the attitude control requirements, I've illustrated it in the diagram, where you see a very simple diagram of both arrays and how they change their pointing requirements in every 6-hour segment of the 24-hour rotational period. In effect, in that period, the whole satellite has to be rotated through 360 degrees, whereas at the same time, the antenna must be continually tilted towards the Earth, which means it has to tilt through effectively 180 degrees of angle. The actual fine pointing of the microwave beam would be controlled by the antenna array itself responding to a pilot signal from the ground station to which it was pointing. Each solar power satellite could beam up to 2 gigawatts to a 4-kilometer wide and rectenna, as it's called, which is a rectifying antenna assembly, which would be located close to a local power distribution hub. So it's convenient in that it reduces the transmission requirements across any particular country. You simply site your ground stations near the center of each power requirement center. Solar power satellites are actually particularly good for countries without any large natural energy resources. And in a paper published by the Korea Aerospace Research Institute a few years back, South Korea was put forward as an ideal candidate for solar power satellites. And a particularly interesting idea was that the rectennas, the ground stations themselves, could be positioned along the 4-kilometer wide demilitarized zone between North and South Korea. Both sides of this zone require up to 120 gigawatts of power, and having a common receiving area for both sides may possibly provide the beginnings of a bridge between these two countries. So although solar power satellites will hopefully provide a solution to the Earth's climate problem in the long term, there is still likely to be localized hotspots in the Earth's surface for some years to come. And we're suggesting that we can address these problems by deploying orbital sun shields. And These would be launched and assembled in much the same way as a solar power satellite. We've chosen a 3.6 kilometre diameter sun shield. This would be capped on segments like the solar power satellite arrays, but in this case coated with a reflective surface to be give total reflection of the sun's rays. The actual deployment is an interesting exercise because what we envisage is that each of the folded spokes, which are launched as 30-meter long assemblies, would be unfolded in pairs. So remember, these are going to be unfolded to 1.8 kilometers length. And they'd be unfolded using the opposing thrusts from the tugs, the space tugs, mounted at the end of these spokes. You would, however, only extend these spokes partially. So we partially unfold each of these segments and spokes. And at some point you would actually then attach a line from each segment to a reel on the end of the adjacent segment. So you have lines, control lines, running from each segment to the end of the spoke on the adjacent segment. And then when all these spokes are in place and all the lines are in place, you would then have a total deployment using all the space tugs operating together, and the whole sun shield will unfurl effectively to the full 3.6 kilometer diameter by the space tugs pulling out the spokes and the reels reeling in the lines to bring the corners of the segments close to the end point of the spoke itself. It's quite a sort of ballet that will be performed in very slow motion with 40 tugs all under remote control. It would be quite an impressive sight to watch this, actually. Now, what advantage does this give us? Well, if we deploy one of these orbital sun shields in a 12-hour orbit, that's at 20,250 kilometers altitude, then each sun shield would provide an eclipse path almost 100 kilometers wide, and the total penumbral shade would last about 26 minutes. This may not seem very much, but if you take a city such as Delhi, population of around 32 million people, the midday temperature has already reached 47.2 degrees C, and believe me, they would really appreciate a period in the middle of the day when the whole city was suddenly cast into shadow. The relief that the population would receive may well enable the city authorities to actually pay for one or possibly more sun shields, so that in effect the project to launch sun shields becomes effectively self-financing. So what other further applications are there for the heavy launch vehicle? I guess an obvious application is point-to-point cargo delivery on Earth. Essentially, you'd be using suborbital flights because you have zero drag at these suborbital altitudes. And as we've mentioned, for the air taxi application. You've got no downwash from the thrusters themselves, so you can land these very large, heavy payloads exactly where you want them, giving you, as I say, a point-to-point delivery. The illustration shows a launch vehicle with 4 standard size shipping containers hung underneath the thrust frame, standard sized but probably much lighter shipping containers. The simple analysis we've done shows that if you use a cruise altitude of 100 kilometers, you can ship a total payload mass of 67 tons over a maximum range of 20,000 kilometers. Basically, that's halfway around the world, so anywhere in the world can be reached from anywhere else, which is a pretty useful thing to be able to do. If you do a simple mission analysis without considering centrifugal force, you can get a flight time of 48 minutes for this range. You approach a maximum velocity of 16 kilometers per second. You limit the acceleration levels to below 1.3 G, and you're left with a fuel margin of 7.5%. Clearly, there's a large number of analyses you can do, covering a variety of one-way and return missions. You can optimize range, payload, and fuel mass. But interestingly, it's worth trading off maximum velocity against both the positive and negative effects of centrifugal force, depending on what your cruise altitude is. So you have a lot of factors here to trade off and play with, and it would be you'd be able to do a number of quite interesting exercises on the software, the Excel spreadsheets that by now I'm sure you have developed and tried out for yourselves. Also, the heavy launch vehicle can be used in support of manned missions by the personal spaceplane to both the Moon and Mars, and we've shown in the diagram the heavy launch vehicle carrying a habitation module to Mars. At the minimum range to Mars of 56 million kilometers, you can transport 50 tons of cargo, and you can land on Mars after a flight time of about 9.5 days. Because it's an unmanned mission, we can accelerate up to a maximum of 2.4 G, and we'd obtain a maximum cruise velocity of 68 kilometers per second. Other space applications of the heavy launch vehicle would involve transport of mining equipment out to asteroids, and particularly in bringing back the heavy loads of the very valuable mined resources. We've proposed that both the personal spaceplane and the heavy launch vehicle can be used to build the first manned base on Mars, and the program to do this is outlined in this slide. You can see a diagram of the base itself with all the various modules, and the actual sequence of flights out to Mars is given in the table below. So the personal spaceplane itself can carry a crew of 3 to Mars, minimum flight time of 11 days, even though we limit the sustained acceleration to 1.2 G because it's a manned mission. But you can see that the flight time immediately becomes suitable for pretty standard astronaut missions. I mean, 11 days is really not very long at all for an astronaut to be in space. The worries about the very long flight times using conventional propulsion all disappear if you use EmDrive propulsion. An important point is that the fuel margin throughout the flight is sufficient for an immediate return to Earth if any problems occur. So this is quite a vital safety function of the mission analysis. If you look at the table of sequence of flights, you can see that we have a total of 11 flights, 9 of which are the heavy launch vehicle and 2 of which are crewed personal spaceplane flights. And the first 2 flights, HLV-1 and HLV-2, would basically take out the minimum requirements for the crew to stay on Mars, which is a habitation module and a fuel store. So these can be simply landed fairly close to each other at the site of the Mars base itself. The third flight, which we've called PSP-1, will take three crew out there. And once you've actually got a crew established in the habitation module, you can start to dock the other modules as they arrive by using the very good maneuverability of the heavy launch vehicle itself. The sequence of events would then be a logistics module and node 1 in the next flight, followed by a second habitation module. The next flight would then be a personal spaceplane flight, which would carry out the second crew of 3. Well, once you've established 6 guys out on the surface of Mars, you can start to build up the Mars base itself. And the next flight, HLV-5, would actually be to put a solar power satellite in orbit, in the equivalent of a geostationary orbit around Mars, so that you've got guaranteed supply of electrical power. And this would be to a rectenna ground station assembly, which the components for which would be sent out on HLV-6. Clearly, the whole rectenna needs to be assembled, and this is where the crew would start to earn their money by going out onto the Mars surface and assembling the various poles and wires for the rectenna assembly. HLV-7 would be carrying an aeroponics module for providing food for the crew. It would also provide a second connection node 2, which would enable further building up of the base itself. An important cargo to be sent out on HLV-8 is an electrolyzer and ice mining equipment. And again, the crew would be employed to go back out to a nearby ice field, mine the ice, bring it back to the base, and use the electrolyzer to top up the fuel store for the Mars base itself, which will then become completely self-sustaining in terms of fuel, in terms of power from the solar power satellite, and also the aeroponics module providing food. The final module that we suggest we'd send out on HLV9 would be a science module, when we can start really looking at the surface conditions of Mars and what we've actually come to look at, really. So we have a 2-year cycle, which would end up with a crew of 6 on Mars. They could then come back and be replaced by a second crew. But the base itself would be fully sustainable, and will form the basis for much further manned missions to Mars itself. We developed the personal spaceplane design to produce this vehicle, which we call a multi-domain vehicle, which is a heavier, more aerodynamic version of the personal spaceplane. It has larger fuel capacity and it can carry a crew of up to 8. It's multi-domain because it can operate in space, in air, or indeed it can land on the water and take off from the water. The original sort of concept was to provide a high-performance rescue vehicle for the regular personal spaceplane space tourist missions that are operating to Earth's orbit or to the moon. And the cabin dimensions are such that, as I say, you can carry a crew of 8, so you can rescue the passengers, the 6 passengers from a personal spaceplane, and still maintain two crew, a pilot and co-pilot. We've got actual cabin dimensions 10 meters long, 3 meters wide, 2.6 meters high. So it is quite a large cabin. It has the passive hatch, docking hatch at the rear, just like the personal spaceplane. But the enlarged nose and tail sections carry additional liquid hydrogen fuel tanks. And if you look at the table below, you can see the mass budgets for both the personal spaceplane and the multi-domain vehicle. So you can see that it's another 5 tons of mass, and we've almost doubled the fuel mass. So this means that if you do an analysis of a moon mission, for instance, you can increase the fuel margin from the original 8.5%, which, if you remember, when we considered the PSP, we were slightly worried that this might be not a large enough margin for a moon mission. Well, you can increase it up to 39% if you use the multi-domain vehicle. It's quite a useful vehicle for many domains, particularly if you look at operation in air, where it indeed is a pretty maneuverable vehicle, shall we say. Further development of the multi-domain vehicle design is a freight spaceplane. This would be a single pilot crew member, and the idea is that this would provide very fast cargo delivery. We can accelerate up to 5 kilometers per second within 15 minutes and put flight times for global distances at around an hour. So once again, we can go from anywhere in the world to anywhere else and deliver, in this case, about 5 tons of payload. Um, so if we have a vehicle which has a single pilot, high payloads and very good acceleration levels, basically up to 9G you can achieve for short periods, then you have a very interesting vehicle. The two-axis engines give very high maneuverability. You've got pitch, roll and yaw, as well as the X, Y and Z translation. It's a very formidable aerobatic vehicle, and it has hover capability, as well as obviously vertical takeoff and landing. So this is a pretty impressive vehicle, and it doesn't need much imagination to think about the possible military applications. This final vehicle that we're looking at is what we call an all-domain unmanned vehicle. And basically, it was inspired by the missions described in various reports of the UAP sightings that are actually being investigated by the Arrow Committee set up by the US Senate now. These missions implied that there was a vehicle, a drone probably, which would fly in space, in air, on the water, or indeed underwater. And it is this underwater capability that really stretched the design of this vehicle. We decided on using small 3.86 gigahertz 4G engines, again two-axis engines, but they only give a specific thrust of 724 newtons per kilowatt. This is because essentially they're using much smaller cavities than the 950 megahertz 4G engines that we've been looking at previously. The payload bay is interesting in it can be used for perhaps long focus optical sensors, or indeed a synthetic aperture radar array, something that's sort of long and narrow. And the main sort of problem faced when you look at the mission, a typical mission requirement, is how you can actually get what is essentially a fairly lightweight vehicle to have sufficient ballast to actually glide underwater. Our solution to this was basically to use the liquid hydrogen tanks, once they'd been emptied on the outward flight, to be filled with the seawater and act as ballast tanks. However, we struggled with the mission analyses a bit and eventually had to incorporate additional ballast weights to basically get the vehicle to submerge. And if you look at the mass budget shown in the table, where we compare the outward flights to the return flight, you can see that down under ballast, we carry 336 kilograms of ballast out on the outward flight, but have to ditch it for the return flight. So it really stretches the capability of the vehicle to carry out the sort of missions that are implied by these UAP sightings. We put some of these mission parameters next to the mass budget table, and you can see that we can look towards a total range of 1,260 kilometers, total flight time of 40 minutes, and we'd be flying at 100 kilometers maximum altitude. Interestingly, the underwater time would be limited to 37 minutes of manoeuvring. You can go longer if you just want to sit in a single place underwater, but we used a maximum flight velocity of 3.7 kilometers per second and an underwater velocity of 35 knots, would you believe? So it's a very interesting vehicle with all sorts of ISR type applications.